Assalamu alaikum. I am Nimra Naseem from the Department of BS Biotechnology and my ID is 22. I am here to present the topic of my presentation, which is Raman Spectroscopy. So, first of all, let me show you the contents of my presentation. First is abstract, then history, then introduction, then principle. In principle, we will talk about the types of scattering. Then types of Raman scattering, then scattering description, then Raman spectrum lines, then Raman shift, and at last conclusion. So first is abstract. Raman spectroscopy is a branch of vibrational spectroscopy which allows an easy interpretation and highly sensitive structural identification of trace amounts of chemicals based on their unique vibrational characteristics. Due to the continuous technical improvement in Raman spectroscopy, an advanced development of the device was achieved and more applications have become possible. And Raman spectroscopy basically involved high energy photons based on the inelastic scattering of radiation in the visible or near infrared region of the sample. Most of the scattered light, like Rayleigh scatter, has the same wavelength as laser source light. There are two types of light scattering, the elastic and inelastic scattering. The elastic scattering is when the photon frequency doesn't shift or change its wavelength. The opposite is the inelastic scattering, which is involved in Raman spectroscopy. The shift of the frequency can be used to get an information about the molecular chemistry. Then history. So the phenomenon of inelastic scattering of light was first postulated by Smeckel in 1923 and first observed experimentally in 1928 by Raman and Krishnan. Since then, the phenomena has been referred to as Raman spectroscopy. In the original experiment, sunlight was focused by a telescope onto a sample which was either a purified liquid or dust-free vapor. A second lens was placed by the sample to collect the scattered radiation. A system of optical filters was used to show the existence of scattered radiation with an altered frequency from the incident light. The basic characteristic of Raman spectroscopy. So, introduction. So, first of all, before going to the main topic, let me talk about the spectroscopy. What is spectroscopy? The study of the interaction of the electromagnetic radiation in all its forms with matter is called spectroscopy. When a beam of light strikes a triangular, it is separated into its various components like violet, indigo, brown, green, yellow, and orange color. This is known as spectrum. Then the optical system which allows production and viewing of the spectrum is called a spectroscope. So our main topic, which is Raman spectroscopy. Raman spectroscopy is a spectroscopic technique used to observe vibrational, rotational, and other low frequency modes in a system. It is commonly used in chemistry to provide a fingerprint by which molecules can be identified. It relies on inelastic scattering or Raman scattering of monochromatic light, usually from a laser in the visible near infrared or near ultraviolet range. This spectroscopy is quite different from other branches of the spectroscopy in phenomena. The other branches of spectroscopy like IR, UV visible, in all of them we study about the absorption of the radiation. The radiation is absorbed by the molecule and it undergoes a transition to the lower limit to the higher limit. But in the Raman spectroscopy, we study about the scattering of radiation. So, what is the basic principle of Raman spectroscopy? The basic principle of Raman spectroscopy is scattering phenomena. So, the diagram, in this we see when a monochromatic light such as laser radiation or any monochromatic light that falls under the UV or the visible region, when it falls on a molecule or a crystal, then the most part of the radiation is transmitted to the molecule or a crystal, while some part of this radiation is scattered at an angle of 90 to that of incident radiation. So here we are not interested in transmitted radiation. Basically, we are interested in scattering radiation. So there are two different types of scattering. First is elastic scattering, which is also called Rayleigh scattering. So in this scattered radiation, we will have same frequency as that of incident radiation. It means there is no change in energy of radiation after the scattering. Such type of scattering in the scientific language is known as Rayleigh scattering. But here we are not interested in Rayleigh scattering. The most of our scattering is elastic scattering. It means most of the light is scattered without any change in frequency. Other type or second type is inelastic scattering, which is also called Raman scattering. When there was a change in frequency of radiation after the scattering, then it is called the inelastic scattering, and it is also known as Raman scattering. Only 1% part of the scattered radiation is scattered by the inelastic scattering. It means its frequency is changed after scattering. It may be decreased or increased. So, Raman scattering is also of two types. First one is stroke lines. So, in stroke lines, what happens when the scattered radiation is the lower frequency as compared to the incident radiation, then it is known as the stroke lines, and we called it stroke scattering. Second one is anti-stroke lines. When the scattered radiation is the higher frequency as compared to incident radiation, then we call it anti-stroke scattering, and the lines we see in Raman spectrum are known as anti-stroke lines. Now we see the further description of scattering, that what happened in the scattering. So in this diagram, first of all, let me tell you what is virtual state. The molecules in the lower state, when it absorbs the incident radiation, it is excited toward the unstable excited state that we call the virtual state. So, first of all, we see the case of Rayleigh scattering, that what happens in Rayleigh scattering. So, in this, the molecules that was originally in the ground state is excited to the virtual state, and when it emits the radiation, then we call the scattered radiation. It goes back to the ground state, so the net energy of the radiation, that the incident radiation to that of scattered radiation are same. There is no change in energy of radiation. So we get the Rayleigh scattering. Then we see the second case, which is strokes Raman scattering. What happens here? In this case, when the molecules that are originally in the ground state, that we call the V0 state, in the ground state, it absorbs incident radiation and goes to virtual state. Now it is unstable state. It goes back to another state, and others, no, it goes back to another state. It is not coming to ground state, it is coming to another state that is above the ground state, that we call the V1 state, or also called first excited state. It's emit the radiation, so now the intensity of radiation is lower as compared to that of incident radiation. It means the frequency of scattered radiation is lower than that of the frequency of incident radiation, so we get the stroke scattering. Now, at last, we see the case of anti-Stokes Raman scattering. In this, what happens? When the molecules is present in the first excited state, it absorbs the radiation and goes to virtual state. And when it emits radiation, it comes back to ground state. It's excited from the first excited state and coming back to ground state. So energy of scattered radiation is higher as compared to incident radiation. It means the frequency of scattered radiation will be greater as compared to that of incident radiation, and hence we get the anti-stroke lines. So next, we see Raman spectrum lines, that what happen in Raman spectrum lines. So in Raman spectrum lines, we see three different types of light. In the middle, we get the high intensity light that are called the Rayleigh lines. And at the equal distance from the Rayleigh lines, we get the stroke lines and the anti-stroke lines that are symmetrically distributed among the Rayleigh lines. On the both sides of Rayleigh lines, the intensity of Rayleigh lines is far more stronger as compared to stroke and anti-stroke lines. It means this Rayleigh light are of very high intensity. But why? Because the most of the scattering is in the form of Rayleigh scattering or in the form of elastic scattering, and intensity of stroke lines is weaker as compared to Rayleigh lines. If we see anti-stroke lines, These are very weak. It means intensity of these lines are very weak as compared to Stokes and Rayleigh lines, because in the original case, if we see that actual condition at room temperature, most of the molecules are present in ground state, and it is very difficult to find out the molecules in first excited state. So it is very difficult to find anti-stroke lines in the Raman spectrum. It gives a very weak signals. So here are the brief description of Raman spectrum lines. Then Raman shift. So what is Raman shift? Raman spectroscopy is an experiment that collects Raman scattering as the signal. When the light passes through the sample, some is scattered as Raman scattering. These photons are in the visible range, but they have lost some energy, meaning the wavelength will be different. The difference in wavelength is called the Raman shift, and it is the same as the difference between vibrational energy levels. This is calculated by the following equation. Delta V is equal to 1 over lambda 0 minus 1 over lambda 1, where lambda V bar is the shift in wave numbers, lambda where delta V bar is the shift in wave numbers, delta lambda 0 is the laser wavelength, and lambda 1 is the scattered wavelength. For example, carbon double bonds have a vibration at 1600 inverse centimeter. If a 514 nanometer laser beam is directed to a sample, the scattered signal will have a wavelength of 560 nanometer. Most commonly, the unit chosen for expressing wave number in Raman spectra is inverse centimeters. Since wavelength is often expressed in units of nanometers, the formula above can scale for this unit conversion explicitly, giving Raman shift in inverse centimeters is equal to 10 raised to power 7 divided by lambda excitation nanometers minus 10 raised to power 7 divided by lambda. So at last, conclusion. So Raman spectroscopy is one of type of vibrational spectroscopy which requires good understanding of the properties of light. It provides a chemical fingerprint of the substance measured and is therefore frequently used whenever unknown material needs to be identified. However, obtaining a Raman spectrum is just the start. After visualizing the data, you need to interpret the Raman image. So that's all from my side. Thank you.